This video is about my experiences with a mains power bank. I've been considering buying one of these for quite some time, largely due to the threat of unstable energy supplies this winter. I wanted something that would power small home appliances such as the Wi-Fi router, and also to see if I could use it to power my boiler, and you'll see how I get on with that later. This particular device is made by a company called Jackery. There are others on the market. Companies such as Bluetti, River and Power Oak make similar devices. This is the smallest in the Jackery range with a 240 watt-hour battery and therefore the cheapest. In this video we'll have a look at the following. Firstly, I'll do an overview of this device and show it loaded up running some small appliances. Then we'll have a look at my attempts to power my boiler. You might find this interesting as there is a particular issue you have to overcome, and that will probably apply to anybody with a modern boiler. Then we'll have a look at charging it from the optional solar panel, and we'll do some experiments with that outside. And finally, we'll have a closer look at the mains output. We'll check its voltage, frequency, and also look at the pure sine wave on a scope. So what exactly is this device? Well, it's a portable unit with a 240 watt-hour lithium battery inside. The lithium battery can be charged from this 8mm DC jack here, and it comes with a 60 watt, I think it's a 65 watt mains charger. There's also a 12 volt car charger, and it has an optional solar panel, all of which connect to this same port. I have got the solar panel, we'll have a look at that later on. So once charged, there are three ways of drawing power back from the battery. You've got two USB sockets here rated at 2.4 amps. That's actually shared between the two sockets. I have tested the output and it will run up to 2.7 amps with no problem, and then it cuts off very abruptly after that. You've got a 12 volt car type outlet here, and you've also got a 230 volt output which can supply up to 200 watts, and it claims to have a pure sine wave output. We'll have a look at the quality of that sine wave at the end of this video. Here I've got the mains charger connected, and if I just go a bit closer to the display, you can see it's charging at an input of 61 watts, and it's currently got 71% of its charge complete. And if I was drawing power from it, you also get an indication of the output power as well. So what I'll do now is take it off charge and just load it up with some small appliances. Okay, so I've now got some small appliances connected to the Jackery. If I just wake up the display a minute, you'll see we're currently showing 33 watts. Most of that is coming from this television here, which is running quite happily. There is a little bit of an overhead, so the TV's probably about 24 watts, I think. Some of the power goes into the inverter in the Jackery. I think if you have it unloaded, it shows about 9 watts with nothing connected, so some of that power is lost in the inverter. I'll now switch on another device. We'll turn on a fan. Probably not a great choice because that's now going to make noise on the video. But it's running the fan quite happily, and we're up to 62 watts there. And my third appliance is a good old-fashioned 100 watt light bulb. I shall enable that. That's the 100 watt light bulb on. And if we the display takes a little while to update, I've noticed. But if we look at that now, we're drawing 150 watts, 151 watts. And very shortly I expect the fan in the power bank to turn on. It does have ventilation at each end to basically blow air across the inverter heatsink presumably, and usually once you get up to about 150 watts it will start running its internal fan. So we've got our three mains powered appliances running there, about 150 watts. I've got a device plugged into the USB outlet, this little desk lamp helping hands thing. I'll switch that on. That's about another 5 watts or so. And we're up to 154 watts. And might as well give it one more thing to do. The phone here, plug that in as well. And see, it should start charging. Not sure if it actually needs much charge, that particular phone. Yeah, there we go, we put another little bit on there, 59 watts. And yes, it's kind of difficult to show as a group, but there we go. That power bank is now running the TV, the USB light, the fan, the 100-watt bulb, and it's charging the phone as well. So actually, for a device that can only output 200 watts, that is quite a useful amount of power. It's currently on 161 watts. So with a 240 watt hour battery, that's going to run for about an hour and a half off a full charge. So here we are in the cupboard for my boiler. The boiler itself is not a combi boiler as such. The top part is the boiler for hot water and central heating, and the bottom part is a storage tank for hot water. So it does store hot water, it doesn't instantaneously heat it. The first thing I had to do was provide a 13 amp connection for the boiler so that I could plug it straight into the power bank. That was quite difficult because this boiler is in an extremely awkward cupboard. There's a very narrow space between the boiler and the door here, and it's also on an angle as well. So the fused spur here used to feed directly to this junction box, which in turn feeds off to the boiler. This is a 5-core cable with live neutral earth and the 2 wires from the thermostat. What I've now done is put a 13 amp unswitched socket below, which is fed from the fuse spur, and that's where the boiler plugs in. So I can simply unplug that and connect it to the power bank, and I'll try that now. So here we are, the boiler is now powered from the power bank. It's drawing about 82 watts. I can hear what I presume is the extract fan and possibly the pump running, even though the boiler is not actually switched on at the moment. But looking at the control panel, we have a problem. There is an error code up, E26, and this red light is a lockout light, meaning that the burner will not come on. Now E26, according to the manual, is an earth fault, so the boiler is not happy with the electrical supply it is getting from the power bank. However, I have got a workaround for that, and I'll try that now. So I've now got my workaround adapter inserted into the power feed to the boiler. The first thing to note is the power has now dropped to something quite reasonable, 15 watts, and I can't hear anything running inside the boiler. And if I look down at the control panel, we've got a normal indication, there's no lockout light, and we're showing the normal display, which is the pressure 1.6 bar. So it's much happier now with this adapter lead, and hopefully I can actually get it to run. If I turn on the hot water and crank the thermostat up, hopefully it will go through its startup sequence. I can hear it clicking, and hopefully in a few seconds time the burner light will come on, indicating that we've got a successful ignition. Just going, I can hear it clicking a few relays, and any second now, hopefully, there we go. The burner is now lit, and that should be heating the water, powered purely from the power bank. Now, looking at the power consumption now, so with the boiler running about 97, 98 watts, that seems quite high. We've got the extractor fan for the flue, and I know for a fact that this boiler has a problem with the diverter valve, so it's probably trying to energise the diverter valve to one end of its travel and failing because it's stuck. So that's probably drawing more power than it should do. I also suspect it's running the pump as well, which it shouldn't be. However, even at sort of 94, 95 watts, it's still going to run for a couple of hours like that, and it only needs about 10-15 minutes to heat a tank of water. So that would still get me out of trouble in a power cut situation. So what was the issue with the output from the power bank that the boiler didn't like, and how does this adapter lead help to work around the problem? Well, I can illustrate it with this plug-in power tester. If I connect this to a correctly wired 13 amp outlet, you see we get 3 LEDs and a continuous tone, and that indicates that it's found the wiring to be correct. If I now connect that to the power bank output, straight away it flags a problem. We've got 2 flashing LEDs and a warbling tone, and that indicates an earth fault, which is also the fault that the boiler had detected. So on this conventionally wired outlet, the tester is looking for 230 volts between neutral and live. It should see 0 volts between neutral and earth because they should be at the same potential, and it should see 230 volts between live and earth. But on the power bank, it will detect 230 volts between the pins that we would normally know as neutral and live. But the earth pin isn't connected to anything. There's nothing meaningful for it to be connected to because the device is portable and there is no reference to earth on either of these two pins. So the tester will see open circuit between the pin we would normally know as neutral and earth, and it will see open circuit between the pin we would normally know as live and earth. And that's why the detector is flagging an earth fault, because it can't measure any potential between these two pins. So how does this adapter lead work around the problem of the missing earth? Well, the socket end is wired conventionally, but the plug end has a modification. I've used one of these clear plugs so that it's easy to see. If I turn it around, you'll see that on the neutral pin we've now also got the earth wire. So the earth and neutral are on the same neutral pin and the live goes to its normal pin. The effect of this is, for an appliance connected to this socket, it will still see 230 volts between the neutral and live pins. It will see 0 volts between the neutral and earth pins because these are tied together in the plug. And now it will see 230 volts between the live pin and the earth pin because the earth is now tied to the same point as the neutral. I've now got the adapter lead plugged into the power bank. If I connect the mains tester to it, you will see that it is now indicating that it thinks the wiring is correct. So it is now happy with the supply, and more importantly, the boiler is also happy with that arrangement. You probably noticed that I've gone to some trouble to label this adapter lead quite carefully. There are some safety risks with it if it got used on a conventional supply. Probably the biggest risk is if you connected it to a socket that happened to have a live neutral reversal. Because the earth is now connected to the neutral pin, if the socket you were plugging into had a reversal, your chassis would immediately go live. There is another risk. If you had a class 1 appliance plugged in such that the load was here and the chassis was connected to earth as normal, as you push the plug into your socket, you don't know which side is going to mate first. If it so happened that you push it in and the live side mates first, then what's going to happen is live will connect through the load of your appliance out to the neutral pin, which hasn't connected yet, back through the earth and onto your chassis. So for a few milliseconds as you push the plug in, your chassis would go live, and it only takes a few milliseconds to get a shock, so that is a risk. However, I'm happy that this lead is only for my own use and it is carefully labelled, and therefore I think it is safe to exist in the world. For this next section of the video, I've moved outside to have a look at the solar panel that's an optional extra for charging the Jackery. I'll perform some experiments on the solar panel, running it directly into a load, just to get a feel for how it behaves, how much power it can supply, and what the effect of covering some of the cells on the panel is. I've also had to record this as a voiceover because I was getting too much extraneous noise outside. So just a quick walk around. Here's the Jackery solar panel folded up. Very easy to put out, just pull the handles apart and there it is out on the drive. And I've got it plugged into the Jackery, charging away, and you can just see, a little bit difficult with the shadow there, but charging at 68 watts. Not bad, free power from the sun. Looking behind the panel, you can see it's supported with its own integral stand there that just folds out from the back. And then if we go to the other end of the panel, there's a little pouch that holds the cable, and also inside that there are USB A and C outputs for directly charging phones, etc. Well, this is my first hands-on experience with a solar panel. It's a perfectly sunny day and I was keen to see how much power I could draw from it. Could I get close to the rated 100 watts? Now, I'm aware that in a proper solar setup, maximum power transfer theory is very important. As the output voltage from the panel fluctuates with the available light, there's an ever-changing sweet spot between the output of the panel and the resistance of the load applied in order to extract the maximum amount of power from the panel. Devices that employ maximum power point tracking are normally connected between the panel and the load. These use smart DC to DC conversion to continually seek that best relationship. Now, I don't have one of these, so for these tests I'll be improvising a load with some items that I had to hand. First of all, I should explain about the electrical characteristics of the panel. The booklet supplied with it says that it has a maximum output power of 100 watts, an open circuit voltage of 21.6 volts, what I assume is the voltage at maximum power of 18 volts, and a current at maximum power of 5.55 amps. So in my first search for a suitable load in the 18 to 21.6 volt range, I found these two 12 volt 50 watt halogen bulbs. Putting them in series forms one 24 volt 100 watt load, so I'll be underrunning the bulbs slightly, but I decided to use this for my first attempt as it still provides a reasonable load and also a good visual indication of the amount of power being provided by the solar panel. So just to explain the setup here, the solar panel is in full sunlight and connected directly to the light bulb load. The power bank is not involved. The meter on the left is reading the voltage across the bulbs. The meter on the right is reading the current through them. So we can obtain the power just by multiplying the two readings together. And at the moment we're getting over 66 watts. Now for my first experience with a solar panel, I was actually quite impressed to be getting this useful amount of electrical power so easily. Next I wanted to try and work out what additional load I would need to get closer to the rated 100 watts maximum. The panel's manual states that at maximum power it delivers 18 volts 5.55 amps. So just using Ohm's law we can see that equates to a load resistance of 3.24 ohms. Now we've already got the load from the light bulbs, and using Ohm's law and the reading straight from the meters we can see that equates to a load of 5.53 ohms. Now admittedly that will change slightly as we go to maximum power. The voltage across those bulbs will drop by a volt or so and the resistance of the tungsten filaments will decrease slightly, but I think that effect will be negligible here. To now find the additional load that we need to connect across those bulbs, we just use the equation for parallel resistances, and rearranging that and substituting the values that we've just calculated, we see we need an additional load of 7.82 ohms. Now that is a really happy coincidence because I happen to have two 8 ohm dummy loads that I made when I was experimenting with valve amplifiers during the lockdown. So I've now added the additional 8 ohm load connected in parallel with the light bulb load, and the big power reveal is 96.5 watts. Well, I'm declaring that a success, only 3.5 watts off maximum, and that could be for a number of reasons. Probably my load is not exactly on maximum power point. I'm also doing these tests on one of the recent very hot days with the temperature in the mid-30s, and solar panel efficiency reduces at high temperatures. This might explain why I'm only seeing 17.67 volts across the panel rather than 18 volts, although that could be due to cable losses. And very quickly, while I have everything still set up, here are the results of varying the load either side of the calculated maximum. My 8 ohm load consists of two 4 ohm resistors, so shunting one out I can apply a higher load of 4 ohms. And although this increases the current from 5.46 to 5.76 amps, the voltage has dropped significantly by just over 4 volts and the total power is only 78.4 watts. Adding more resistance in series, at 12 ohms I get 83.9 watts and at 16 ohms I get 81 watts. And yes, the load resistors did get hot, but not excessively so. The light bulbs were far hotter. So another thing I'd heard about solar panels but not really experienced was the issue of shading the panels. That it's very important not to have any of the individual cells shaded because they're all in series. I just wanted to see the effect of that for myself. Now here's covering a quarter of the overall area of the panel. And as you can see, this had a dramatic effect on the power. We're down to only half a watt there. If I now adjust that and cover 1/8 of the panel, we get some of our power. We're back to about a quarter of the power we had originally. If I now adjust and just cover 1/16 of the overall panel, that's 2 of the cells, and we're now back at almost half, or about half the power we had originally. And clearly if I now restore full coverage, we're back to our 66 watts. So yes, the effect of shading on any part of that panel is quite dramatic and something you'd have to avoid in a full setup. So I just want to do some tests on the 230 volt output from the Jackery. We'll have a look at its voltage, frequency, and also in a moment I'll have a look at it on scope to see what the pure sine wave AC actually looks like. So at the moment, as you can see, I've got the voltmeter plugged in and we're getting 229 volts approximately. It's changing a little bit, jumping up and down by sort of half a volt or so. I did wonder if that was because there was no load on it, but actually if I switch on my 100 watt load again, it doesn't really change its output behaviour. It stays in the sort of 229 volt region, just jumping up and down by half a volt or so. I'll turn my light back off and just change over to frequency, that one, and we're getting 50.2 hertz. Not a problem, that's pretty close to mains. Would be a problem on the national grid, but not a problem for general use at home. If I switch the light back on, so it's another 100 watt load again, and the frequency does not change. So I'm now going to have a look at the mains output from the Jackery using my picoscope. This isn't really a proper scope, it's a USB device that plugs into a laptop, and I'm using a sacrificial Windows XP laptop here just in case anything goes wrong. The other issue with this is we've got a 20 volt peak maximum input, so I've got to find some way of taming down the 230 volt output from the Jackery. And also, just to bear in mind with doing measurements on mains type voltages in this way, you have to be very careful that there are no earth references anywhere. Now, we said before that the output of the Jackery is very much like an isolating transformer, so I'm reasonably happy that there's no problem there. And also the laptop is not earth referenced at all. It is running from the mains, but it's on a power supply that's only got a 2-core lead. So to reduce the voltage down to something that's safe for the picoscope, I've got a little resistor network here. We've got 200k in series with 10k, which I'm measuring across, and a little bit of calculation here. That should give us 10.95 volts RMS, 15.4 volts peak, and that's within the range, the 20 volt range of the picoscope. So we're now looking at the output of the scope, and I'm going to switch on the output of the Jackery. Here we go, and we've got a reasonably nice sine wave. Looks very clean, no issues with that at all. If I go down to the measurement section at the bottom of the scope trace, I hope this stays in focus, you can see we've got 10.9 volts AC there across our little resistor bridge, which is very close to what we calculated actually of 10.95. We're measuring a frequency of 50.2, 50.3 hertz, which is close to what we saw on that plug-in meter, which was 50.2 hertz that was showing us. What I'll do now is I'm going to turn on my light bulb load again. I've actually changed the load. We've actually gone up to this lovely 150 watt Osram clear bulb. I'm going to switch that on and then go back to the scope. That was it going on there. I don't know if you can see, there's a little bit of distortion has now crept into the sine wave just on the, like a mouse close to it, just on the rising and falling edge. You've got this little strange notch has appeared. It reminds me very much of crossover distortion in an amplifier. But other than that, the sine wave is not affected by the load. It's just that little bit of distortion. If I remove the load now, I'll just switch it off, you see it cleans straight back up again. Well, I hope you've enjoyed this rather rambling look at the Jackery mains power bank. This particular one is the Jackery 240. It's the smallest in their range, 240 watt hour battery. But I have to say, after playing around with it for a few days, even a small one like this is actually a very useful device. It will power my boiler, it would power the router, the Wi-Fi router, for a long period of time. And I think over the winter, if we have power shortages, this type of device is going to become very popular. I would definitely consider buying a larger, more expensive unit